Okay, good morning, everybody. Thanks for coming. My name is David Sanders. I'm an associate professor at the National University of Mexico in the Faculty of Sciences, and I'm currently on sabbatical here in the Julia group at MIT, just down the corridor. So this workshop is supposed to be a continuation of one that I gave last year at JuliaCon called Invitation to Julia. So as you see, the first notebook is called Re-Invitation to Julia, where we'll just do a really quick sort of high-level overview of some sticky points, maybe. And so the idea of this workshop is to get past this sort of basic syntax stuff and into some of the more interesting parts of Julia. So mainly, how to define new types, especially with type parameters, parametric types, and then metaprogramming, which is this sort of big subject that everybody's a bit scared of until they do it, and I was too. And so my qualifications for giving this this workshop today is basically that I've been developing a couple of packages, and so I've come across all of these problems, and I've learned something about how to solve them. And so I'd like to actually give a case study that came from a package that I just published recently about a real application of metaprogramming to something useful. And probably we won't have time to talk about anything else. So please feel free to interrupt and ask questions. That's why we're here. Any questions to start with? So this repository with the notebooks is on GitHub at this address, github.com/dpsanders/intermediate_Julia. And as I was saying just now, you can clone this straight into JuliaBox if you don't have a working Julia installation on your local machine. Okay, so let's get started with the first notebook. So I'd like to just say that I've got various sources of financial support from my university with these grant numbers and a CONACYT sabbatical fellowship, and I'd like to thank the Julia group here for their hospitality during my visit. Okay, so let's just very quickly go over some important points of the basic syntax and some other things that are not so basic. So to get started, we need some variables. So if we just introduce the variables with a standard kind of assignment syntax, and then we see that they have this type associated. So types are crucial in Julia. They can often remain hidden, but we'll actually be seeing more along the lines of when we need to think about types more carefully. So I've got two variables with two different types, and then I add them together, and magically it knows what to do, it being Julia. Julia is an inanimate object, so in English we call it it, not she or anything else. Okay, so what does this do? We can ask Julia, we can introspect with this @which macro. And what we see is that it's calling plus with two arguments. So plus is a function, a generic function, and it has lots of different, as we can see by just asking Julia what plus is. It says it's a generic function and it has lots of methods. And those methods are these versions of the function that make up a tapestry that sort of covers the world of things that you might want to add. And we can click on all of these links to find out where those are defined in the Julia source code. So I guess this is a review for everybody, but let's just do that. And so we can actually go in and see where these are defined in Julia code. And so a lot of these things are going to be quite low level, and so they're just going to call straight into some low level thing called LLVM that we won't talk about. So if you want to know about that, you should be in Arch's talk right now, or look at it online later. Okay, so we have this generic functions with lots of methods, and we can ask Julia which method it's using. And tomorrow we'll see that a very important recent development that we can now just step through what exactly Julia is doing when we call a method by using the debugger in 0.5, in version 0.5 of Julia, which is hopefully coming out soon. And we can do that right in the Juno IDE. So Mike Innes will show us that tomorrow. Okay, so Julia has this reputation for being fast, and it's a well-deserved one, but it's not always fast. So it's quite easy to write slow Julia code if you're not careful, but you just have to look after a few details, and then your slow code will magically become fast. So we'll see that in a minute. And so let's define a function. So why, in some sense, why is Julia fast? Or so Jeff has a nice talk about that somewhere, Jeff Bezanson. So let's define a function. We have this nice one-line syntax for simple functions, and we can call that function with 2 integers or 2 floats, and we get an integer back or a float back. And so we can actually see all of the stuff that's going on underneath when we do this with these macros. So macros are these sort of special kinds of functions that we'll talk about later with these @ symbols in the name. So the first one is @CodeLowered. So that takes our function and sort of makes it into a more low-level version that's still valid Julia code. So this is sort of somehow the actual internal code representation of that function that we just defined. So it's already parsed what we wrote into an internal representation that we'll see later. And then the next step is that it assigns types. So this is, in some sense, sort of one of the key moments in Julia when type inference is done. So it looks at the code and infers what are the types of all these objects. And so we can see, if we are eagle-eyed enough, we can see that everything here is an integer. Okay, but it's pretty difficult to see that because there's too much noise. So instead, we'll use this other macro called codeWarnType, which cleans up the noise and just leaves us with the meat. And so we see that there are 2 variables in this function, x and y. They both are inferred as being integers, and the code got kind of simpler to understand. So there's this box thing that means some internal representation, and so this is, again, valid Julia code in some sense, and it's telling us that Julia successfully inferred the types of all these objects. Then the next level down is this LLVM, which is an intermediate representation between the high-level Julia code and the low-level machine code. So it's still kind of possible to understand, at least this simple function. And you can see that it's doing something very simple again. And we can see that if we call it instead with an integer and a float, it's doing something more complicated. Doing something more complicated than what it did with just 2 integers. And so then we can go down to the final level where LLVM has compiled this intermediate representation down to machine code. And we can actually see the assembler output and again see that it's doing different things for these 2 different methods. Well, no, sorry. For these 2 different specialized versions of the function. And so this is sort of the key point that we have. This is the actual machine code that was generated, that's run when you call this function with those arguments. And it's been specialized right down, so every single version of this function for any combination of types gets its own specialized bit of machine code that's very efficient. And if we do this mixed type, then it's doing something more complicated because it has to do this conversion between an integer and a float at some point. And that's a complicated operation, as we'll see in a minute. Will we? Yeah. Okay, so this code is nice and efficient. You can see it's very compact, even if you don't understand the machine code, which I don't. And so let's do a different function. So here we have a function that has a variable a, which starts off as 1, so it's an integer. And then we're going to add x to a and return a. Another simple function. So if we pass an integer in, again, we see that everything's nice and simple. And it correctly infers all the types. Let's do codeWarnType. And it correctly infers all the types. But if we do codeWarnType on g of 3.5, so it's a float, then we see this bad news. Right? So this is the cause of all our troubles in Julia as regards many of our troubles in Julia as regards speed, when it cannot infer the correct type. And so we see that we've got this any, which is telling us that there's something going on such that Julia is unable to assign a unique type to A, to infer the type of A. And we see that this line has suddenly become much more complicated because it's flipping. So A is flipping, started off as an integer and later became somehow a float. So it's flipping between integer and float. And when we look at the native code, if we pass in an integer, again, we get something very simple. If we pass in the float, we get this big mess. So it's not that complicated, but it's certainly much more complicated because there's this conversion going on in the middle, which is the complicated bit. And so you might think that this is such a simple function that Julia should be able to optimize this and realize that all it needed to do was make that integer 1 a floating point, 1.0. But those are the kind of compiler optimizations that have not yet been implemented but should be in the future. And so we have this idea, this concept. This is all summarized in the concept or the name that people use called type stability. So that's sort of a maxim that says that if you want efficient code in Julia, you should make sure that your variables or your functions are type stable, which means that no variable changes type in the middle of the function. And if you do that, then you hopefully will have efficient, fast code. Okay, any questions? So I'd like to just say a couple of words about arrays. So people often create array, which is another fundamental building block in Julia. So actually, Julia has a very sophisticated array machinery, which is becoming even more sophisticated, as Tim Holey will tell us in a couple of days. So how do we make an array? In my opinion, the sort of the clearest way to do that is with this zeros function. So we're going to set up an array of zeros. So you can define arrays which are uninitialized, but I prefer to use zeros myself. Okay, so we just put zeros and we can give it an optional type, and it'll make an array of zeros of that size. So here we just have one number 3, so it makes an array of 3 elements. And we see that array is a parameterized type. So it has, this is our first parameterized type. So it has these curly braces, and inside the curly braces there are two parameters, one of which is a type and one of which is an integer. So the type tells us the element type, the type which every single element of the array has, and the other number tells us the number of dimensions of the array. And note, that the length in each dimension is not included in the type information. So again, if we do 0s, 3, 3, then by default it creates an array of floats, and here we have 2 dimensions. It says rank 2 array, and so that's what this 2 is here, and so we get a matrix. And if we actually want the length in each dimension, we use this size function, and that returns a tuple, a tuple, an ordered pair or an ordered n thing, an ordered thing of length n. That's another important type in Julia. And one-dimensional arrays may be extended by using this push exclamation mark function. So exclamation mark is a convention in Julia to say, just a convention to say that one of the arguments of the function is actually going to be modified. In this case, the array has been modified in this operation. So I actually added an element to this array. So any one-dimensional array can be extended in this way. Higher dimensional arrays have a fixed size, however. So if you want to have a matrix that grows, then one way to do it is with a vector of vectors. So we can write that like this. So this is a strange notation. So if I just put, some w equals square brackets, then we see that creates an empty array. But what is the type of the elements inside the array? We see that it's any. So that array can actually contain objects of any type. For example, I can put in the string David into W, or I can use this append. Well, yeah, let's say I can push that in, and then I can append an array of other things. And then we can look at W, and we see that we've added all those things. So those are two different ways to add things. Push adds elements, and append adds each element of an iterable object. So this different syntax means make an empty array, but each element of that array is going to have this type that comes in front of the square brackets. So in this case, it's going to be a vector of ints. So what is a vector of ints? Well, again, we can ask Julia what it is. And we see that it's just a type alias, another name for array of ints 64 and 1. So int and int64 are the same on my machine. On a 32-bit machine, int would be int32, a 32-bit integer. So once I've got an empty array, then I can push things into it, and what I'm going to push into it are integer arrays. So if I do that, then V becomes this array of arrays, a list of lists, or a vector of vectors. We don't use the word list in Julia, sorry, that's a Pythonism. So, so we get an array of arrays, and then we can convert that to a matrix with, let's see if I can do that. So we use hcat of this V, and we need to do this splat operator. So hcat concatenates horizontally, that's where the name comes from, horizontal concatenation, and this splat means take each element of the array and put it as an argument. So we could do hcat of the first thing in V and the second thing in V, and that would give us, we horizontally concatenated these vertical vectors. That's how we can think about it. So another way of writing that is m equals hcat of V splat. So that takes each element in the iterable and sort of makes it another argument of the function. And then to get it back to the form that we had in the original vector of vectors, we might want to transpose it with this prime. And then we get exactly this format that we had before. We have to be a bit careful when we're splatting large objects, objects with many elements, because that's slow. And so then you might want to use a different method. For example, you could just make one huge vector, just concatenate things into one huge vector and then do a reshape. Okay, and so in Julia 0.5, I think there'll be a reshape, which is just a view onto the array instead of a copy. Okay, and in Julia 0.4, we can actually write this in a much more simple way, like this, where we specify the type, and we just write this out. But so that works in. Sorry, in Julia 0.4, we can write that as like this. In Julia 0.5, we'll be able to remove this because the syntax has changed to what you think it should be, and now this will make an array of two arrays, whereas in Julia 0.4 it currently does a concatenation. Hope that was clear. Okay, and so to finish this little first review, let's talk again about performance. And one of the big gotchas for people who are starting out with Julia is programming in global scope. So that means not inside a function. So here's a little simulation I did. There's just these 15 lines of a random walker moving around, and we want to do some statistics about that random walker. So at each step, it jumps left or right, and the quickest way I found, almost the quickest way and most readable way I found to do that was this if else, which is a function that takes a Boolean and tells you what happens if this Boolean is true, which is this -1, that's step left. What happens if it's false? +1 step right. So I'm adding onto this pos, which is the position of the walker, which lives on the integers in one dimension on a line. And I'm just doing a couple of nested loops. And so we can just wrap all of that in this @time macro so that, So the @time macro is the standard way in Julia to time things, to time how long a piece of code takes. So here I've got a piece of code, I wrap it in begin end to make sort of one block, and then I time it. And let's do that. And it's going to take a while. And so, so this is the standard kind of code that you might write coming from one of the other languages. So I'm going to try not to mention any other languages today. I don't want to make any comparisons. You'll just be able to see for yourself, what the comparisons are. So coming from somewhere else, you might write something like this, and you'd be quite happy. Oh, it's 13 seconds. That's pretty quick. But then, how do you know if it's quick? So you would have to go away and write some C version or some Fortran version, which we don't want to do. And so instead of looking at the time, the absolute time, let's look at this instead. So it's reporting how many allocations it's making, and it's making 380 million allocations. So it allocated a total of 7 gigabytes. So that doesn't mean it's using 7 gigabytes of my memory. It means it allocated a bit and freed it, and then allocated a bit more and freed it. So in total, it did this amount of memory allocation, and that's an expensive thing to do. It takes time. And then it ran the garbage collector. That's what GC means, some large fraction of the time. But this code shouldn't be doing basically any allocation at all, except in this array that I'm adding things to. And so this is a flashing red light saying there is a problem in this code. And that problem is, again, type stability. But now it's the fact that we're in global scope. That's all. That's the reason for the type instability. There is no other type instability here. And so the point is that the global scope is potentially infinite. And later on, some of these variables might change type. And so Julia cannot decide what type they are. So this is a current limitation that will be removed in the future. But currently, you should never write in global scope. And in the future, you should never write in global scope either, even when you can, right? Because this code is actually hard to read. So let's refactor it into some functions. So there's this rand bool that returns a true or false. So bool is Boolean. So I'm just repeating that cell. That's Control-Enter in the notebook. True or false, true or false. Okay. So I just refactored into 2 functions, one that runs one single random walker, and then one that does the loop over different walkers. So now I can pass in these things as arguments. Now the code is completely readable. I don't need any comments to tell me what this code is doing because I have these nice variable names that tell me exactly what's going on. Okay, so now we've wrapped everything in a function. And so the first thing we have to do is warm up, as people say, the Julia, let's say. So what does that mean? It means we have to run the function once with very small values. Oh, sorry, I didn't actually run the cell. With very small values of these parameters. And what that does is compile the code. So what just happened was that this code got compiled down to machine code. So I could do an @code. Well, let's do it. I can actually do @code native and see the machine code that got produced. So it's pretty long. Not that long. So that's the machine code for this operation. And so that just happened when I ran that cell, this cell, it compiled those functions with these input types, integer and integer. And so now we're ready to do the production run, which is actually do this calculation with the serious number of things. And so this is the answer. So it takes 0.28 seconds compared to 13 seconds. So it's a factor of 60 or something. Yeah, about 50 times faster just from wrapping everything in a function and making it look pretty. So that's a really important lesson. Yeah. Okay, good idea. So the question was, if I do @code warn type, so if I don't repeat the question, please remind me to repeat the question. Okay, so if we look at these variables, we see that they were all correctly inferred. There are no any's anywhere. So the base dot boxes are nothing to worry about. What we have to look at is basically this information right up top that tells us which variables did not have a unique type assigned. And then once we've found those variables, then we look through the code and we try and correlate that with the original code that we actually wrote and work out where this type instability is being introduced. But we don't actually have to look at any of that because just from looking at this first bit, we can see that nothing bad happened, let's say. So good question, thanks. So yeah. So I'm not saying that this is the best code to do this particular problem, but I'm just saying it's a pretty efficient version. So if somebody wants to knock up a quick C or Fortran or whatever version and compare the timing, that would be nice. Okay, so the other day there was there are various fora now where you can ask questions about Julia. So in one of these, somebody said, oh, but you're not supposed to use global variables, and you used a global variable in your answer. And so you can use global variables as long as you declare them as const. And so what that does is it literally makes them constants, and so then Julia knows that the type of this object is not going to change. Right? So actually, if I make it, try and assign it the value 10, then it says that's invalid. I can't redefine it. So Julia now knows that my number is a float and will remain a float forever, and so it has inferred the type. Now you might have, there are in your packet, if you're writing some piece of software, you might want some kind of global variable that has some kind of global state that doesn't really belong anywhere else. And there are two ways to do that. One is like this. You make an array. It's a sort of a hack. You make an array with one thing inside. And so it knows that state is always going to be an array of that type. If I try and change it, it'll tell me that I can't redefine it. But what I can do is say that state 1 equals 10. So I now actually modified the inside of this object. So it's only the sort of outside layer of the object that's constant. The inside can be changed. And so that's a way of having a global that is type stable, but it can be changed. And another way would be to define a type and make an element of that type constant. So let's say my type, which has an integer inside, and then I make my global equals my type of 3, and then my global.x equals 10, and again I changed the global state that's stored in this thing, which is a constant type. So we could say that this is a temporary situation, and at some point this will get cleaned up, I think. Okay, any questions before we go to the meat?
I guess about the box, the appearance of the box in that code.
Yeah.
The last question. What is that indicating? It's indicating. What's the relation of the box and the any?
So the question is, what is the box in that code 1 type indicating, and what is the relationship with any? And the answer is, I'm not the right person to ask. I don't know. I don't understand that level. But it's a good question. Okay. Can we go on? So, what time did I start? Like 9:10, no? 9:15. Defining new types. So this is a very common thing to do in Julia. Basically, we have lots of types in Julia that are all predefined. And so in other languages, predefined types are special. In Julia, predefined types are not special. We can define types that are just as good as anybody else's. Even, integer. So we can define our own kind of integer type that even is just a representation at the level of bits. And it'll be just as good, by which we mean just as fast, basically, or just as powerful as any other type. Because all of the integer types, as we saw briefly, well, we didn't really see that, but they're all defined in some sense in Julia. Okay, so what we're going to want to do is, so I'm going to actually, what I'd like to do is take sort of the simplest example of defining types and gradually make it more complicated. And the simplest example of defining a type is just a wrapper around, let's say, a floating point number, or some number. So we're going to have a type that just has a single number inside. And when I was preparing this, I thought, oh, but that's so boring. And actually, it turns out that it's not. It basically, you can see all of the complexity, well, not all, but a lot of the complexity of types in Julia, you can see with just this simplest possible example. And this is actually a real-life example that came out of a package that I mentioned that I recently published called Interval Constraint Programming, which is a pretty bad name for a package, maybe. But so I'm not really going to talk about what that does until later. But basically, we want to calculate the volume of objects, cubes, basically, want to calculate the volume of squares in 2 dimensions, cubes in 3 dimensions, pieces of line in 1 dimension. So it's what mathematicians would call a Lebesgue measure, but I don't really want to use that name, so I'll just call it a volume, even if it's in 1 dimension. So let's define it. So this is how we define a type in Julia. So we might have the word type here instead of immutable, and then we could modify the contents. But I'll put immutable, and then we won't be able to modify the contents of this object. That's what immutable means. And so we're defining a type called vol, which is going to represent one of these volumes of something, and that has a value, which is the magnitude of the volume of the thing. So this is just representing, the magnitude of the volume of something. And so when we define that type, what are we doing, really? We're sort of defining a box. What are we actually defining? So before I ran this line number 2, before I ran that, we had just an idea of what a thing of type vol looks like. So it's sort of a template, which is a box, and it has one little piece of information inside. And so I can make as many copies of that template as I want, just as if I were making cookies with a cookie cutter. And so, I can make an object called v1. Well, let's call it v because I've got v later. So I can make an object called v, which is the volume of one object, and an object and a variable called v1, or I don't know, w, which is the volume of another object, which is 10.5. And so now I have 2 copies of this object. And so this vol of 3, what's going on there, it looks like a function call. And it is in fact, or at least we can think of it as a function call. And so what happened was, just as in some other languages, there is, when we define a type, automatically there are some constructors created. So a constructor is a function that makes an instantiation, an object of a given type. And so those are created automatically, and we can see that with this methods call. So if I do methods of vol, we can see listed what options we have, which functions have just been created to make objects of type vol. And you might think that we don't understand much there. So let's go to Julia 0.5, in the development version. So if we do the same, just going to copy over that over here and then do methods of vol, and we can see that the output is actually much more readable now. So what it's telling us is that automatically there were these things created. A function called vol that takes one value that's a float 64, and a function called vol that takes a value that's not a float 64. It's just, so let's recall that this : is a type annotation. And so here it means that first method listed, this first method listed, will work with, will accept a variable of type float64, whereas the other one will take a variable of any type at all, apparently. Right? So here, for example, we passed any type at all. We passed an integer, and what happened, actually? It ended up as a 3.0. Why? So it ended up as a float inside the vol, because I defined vol as having having to have a float 64 inside, but magically this 3 got converted into a float. So there was actually an implicit call to convert. So there's this important function called convert in Julia, and there was an implicit call somewhere inside Julia. So after you go to the debugger session tomorrow, you'll actually be able to follow through and see exactly what happened in that process. So you could do it by hand, but it's a bit painful, so it's easier to do it with the debugger. Okay, so of course I could also do this, volume of David. So, should be, I don't even know what will my volume be, but of course, what's going to happen? Convert, so I said there was an implicit call to convert. So what's happening? It's trying to call convert of this string that I typed in, this ASCII string, to the type, to type float64, right? So this is a sort of strange notation. So this is the code that it's trying to do. Sorry. So that's the way of writing, that. So it's trying to do that call. Convert to float64 the string David. And that doesn't exist. And in fact, I can't even do convert float64 the string 3.5. So if you want to do that, you have to use a different function called parse, and then it works. So convert just literally converts between one kind of compatible type and the other, whereas parse is actually trying to change a string into a float64, which are very different kinds of objects. Anyway, that's a detour. So the point is that, because I have this function that takes any kind of object, this doesn't immediately throw an error. It throws an error inside this process that's trying to make this object of this type with this thing inside by doing this explicit conversion. Is that clear? Okay, so now I have this object v, right? Let's remind ourselves what it is. Okay, it's a vol and it has 3.0 inside. So this is the default way that Julia displays objects of a type. I can find out what is inside this type in several ways. So if you're doing this interactively, the easiest way is v dot and then the tab key. And that will auto-complete whatever's inside. And so if there are several things, it'll give you an option, a little drop-down menu with the options. And so what's inside is this value thing, which is 3. And if I try and change that to 10, it'll give me an error because vol is immutable. It cannot be changed. So another way to do that is there's field names of v. That will give me a list of all the fields inside v, the names of them. And those names are going to be these symbol types they're going to be objects of type symbol, which we'll come back to later. So basically a symbol you can think of as kind of a string or something. It's called an intern string, whatever. It's sort of a string with that's not really doesn't need to be compared as a string or something. Anyway, okay, so we can access this value of this thing inside the object in several different ways. We can do the standard v.value, or we can do something that's more useful, if you're doing some kind of, if, for example, you don't know exactly what's in your object because you read it in some script from some database or something, you might not know exactly what there is inside, so you do field names of the object to see what there is inside, and then you can iterate through those fields, and so then you'll use this get field v, :value. So that gets the field of v with this name. You can also do it by number, so you can get the first one, then the second one, then the third one. So these are useful, for more advanced applications. And as I said, you can't assign to something that's immutable. Okay? Clear? So far we've been using these default constructors that magically appeared when we created this type. And as I said, we can just see those with methods of vol, and on Julia 5.5 that's clear. And we have a problem now, because we could do this, volume of -1, and it'll do it. So it'll create something with a negative volume, and we know that doesn't make any sense. So what should we do? We should prevent it from ever creating an object of type vol, which has a negative value. And the way we do that is sort of intercepting it before it creates the type, and allowing us to create the type, for it. I mean, allowing us the control to create the type in the way we want. So this is we're going to be redefining this type lots of times in this notebook. And so every time we redefine a type, we can't redefine types in Julia. If I try and do that, it gives me an error. I just, it's not giving me an error. That's strange. Any clues what's going on there? Okay. Usually it gives me an error when you try and redefine a type. So anyway, so you do this workspace parentheses command, and that will clear the workspace. So it'll sort of just undefine all the things it would have defined. So common question is, can you clear a single variable? And the answer is no. You can only clear everything. Okay, so what have we done here? Inside this type definition, we have declared, we've written a function with the same name as the type, and this is actually going to be the constructor. And so in this function, which is called an inner constructor because it's inside the type, we can do checks on the value that we're taking in, and do things based on that. So for example, we could check, is x, this argument that we're passing to this function, is it a real number? If it's not, then we're going to throw an argument error, must be real number or something. Okay, so what is this strange syntax? So x less than colon means x, no, is that true? Can I use that? 3 real? No. Okay, that's not the right syntax, sorry. Is a x real? Is 3 a real number? Yes. So is a x real? Vertical bar, and then we're going to throw an exception. So what is this strange syntax? It's called short circuit evaluation. So I put a link to the page of the manual that explains it pretty clearly. So this and is saying this thing is going to be true only if, this line is going to be true only if x is less than 0 and this other thing happens. And so the idea is it evaluates the arguments one by one. So if x is not less than 0, in other words, it's non-negative, it's positive or 0, then it will never actually reach this other bit of the expression. It will never evaluate that. It will short circuit the evaluation. It will just break the evaluation and go on to the next line. And so it will only reach this if x is less than 0. And so this ampersand acts as if it were an if-else. Sorry, an if-then. And this OR does the same, except that it uses OR logic. And so, if x is real, then it knows that the Boolean OR is already going to be 1, and so it breaks the evaluation. If this is false, then it goes on to do this. And this throw is throwing an exception, so it's like throwing an error, basically. And I give it this argument error, which is actually a type, and I pass a string in that's going to be the error message. So if I do that and I create some of these things, so if I pass in now my name, my string, then I get this error must be real. So this is the way that you can pass information to your users about exactly what error they did, they made. Or if I do vol of -3, then I get the different error message. So is that clear, this short circuit evaluation? So any questions about that? That's very idiomatic in Julia. If you look through the Julia source code, you'll find this used a lot. So some people don't like it. There's some discussion on GitHub about alternative syntax for this thing, these kind of things. But for the moment, it's here to stay. So we just have to. So the most common one is this and. So it's if this is true, then do that. And it's a sort of control flow operation. So for example, if x is less than 0, then return. That would be a pretty common one. Sometimes you might need to put extra parentheses around the condition. Okay. So that's an inner constructor. So we now have a way to control and not allow objects to be created that violate some condition that we want to impose. But unfortunately, there's a problem with that. Is there? Oh no, not yet. No, that's okay so far. Yeah. Okay, so now comes the more complicated bit, which is what happens when these types become parametric. So what does that mean? So let's start again. So we might not want to insist that the volume is a float 64. Maybe we live in a world where everything is an integer, so it doesn't make sense that volumes are float 64s. The volume of a cube that's 1 by 1 by 1 should be 1. It shouldn't be 1.0 necessarily. And so we might want to store any kind of volume in there, at least any kind of, let's say, real number, for example. And so you might think, oh, okay, I'll just leave off this type annotation of this value variable inside the type. So if I do that, then I could just stick anything in there. Right? So I could stick 3.5, or I could stick 3. And they both work, and they give different, it seems like that's something useful to do. It's not that useful, of course, because I can also have, sorry, I'm so used to doing these things in Spanish. So I can also stick a string in there, and that doesn't make any sense. So I could do one of these checks that we just did. But the real answer is that this is the wrong thing to do. So basically, inside a type, unless we really, really know what we're doing, we should never leave these variables without type annotations. Why? Because of type instability, again. So we'll get something that's very slow. Why is it slow? Because basically, what it has is a box. So this is to do with this box that we were just discussing. This object will be represented, instead of just a little string, a little bit of memory with the number in, so the integer or whatever, it will be represented as a box with a label that says, okay, currently I have an integer, and then a pointer to the bit of memory, which is the integer. And so this is obviously going to be much more inefficient than just having the integer in there, especially if it's an immutable, which means it can be stored I always say on the stack instead of the heap. Okay, so that's the wrong way to do it. What's the right way to do it? And the right way is this parametric types. So what does that mean? So it has this syntax. So vol, curly brackets, braces, curly braces, t. And then value, colon, colon, t. So what is t here? Well, we don't know what t is, and that's the whole point. So this is a syntax that says vol is going to be a type, but actually there's this extra thing called t. And so if t is an int, then I'll have a vol of an int, which has a value which is an int inside. If t is a float, I'll have vol of a float, which has a value which is a float inside, etc. And so what this is actually saying is, okay, I've actually got a template of a template in some sense. So, before we said that a type was a template, was the shape of the box and the shape of what's inside the box. Now we have a sort of meta template that's saying, okay, to make a template, of type with type t inside, what I do is I have the sort of global template with any type being able to be inside, and then I make this one, and then I can instantiate it or something. Okay, so it's basically there's a missing quantifier that says for all types t, define a volume in this way. And so when we try and create a volume with a given type inside, it will make that particular one. That's the idea. So there's a potentially infinite number of types here, which will never get realized, because we'll only ever create a finite number of different volume types with different things inside. Okay, so how are we going to use these? So we do it exactly the same way as we've been doing, except that something new happened. So I put vol of 3, and we see that it automatically recognized that 3 was an integer, and so it automatically chose the right type to go inside this parametric bit. And if I do the same with 3.5, it's creating an object of a different type, right? This is actually a different type of object. It's a vol with this parameter inside, which is now float 64 instead of an int 64. Is that clear? Questions? So if you understand this, this is the whole basic thing is understood, and then it's fine. So if I do vol of hello, I haven't put any constraints yet on the type t, and so it works. So it has vol of type ASCII string with this thing inside. But exactly, we don't want to allow that, right? So we have to start doing some restrictions. We have to impose the restrictions that we want. In this case, the volume should be a real number, let's say. And so how do we do that? We use this extra syntax, that less than colon, which says that we're only going to accept types which are subtypes of real. So for example, int is a subtype of real, which means mathematically that integers are real numbers. Each integer is also a real number. So mathematically, you could argue if that's strictly true, but there's some sort of canonical way of mapping the integers into real numbers. And so in Julia, we're just going to say that any integer is a member of the sort of set of real numbers, which doesn't ever exist, doesn't ever get instantiated. And float 64 is also real, and other things are as well, like big float. And also there are some abstract types like integer that are also subtypes of real. Okay, so any of those will be okay, but they have to be concrete types. Anyway, so is it clear? So we're only going. So this is saying for all t, but only those t which are subtypes of real, we're going to allow us to create this type. Sorry, I need a workspace. So there was the invalid redefinition of the type coming up. So I need this workspace to clear everything out. Now I can redefine it, and now I can try and define this volume with hello. Yeah. So that gives us an error that's slightly strange. We'll see why that is in a minute. But if we go back and put in a real number, then it does work as it should. So now let's do the inner constructor again, right? Because we're trying to build up this type into something useful. So we had an inner constructor before. Now we've got the parametric type stuff. Now we try and put them together. So so a parametric type with an inner constructor. And this is where everything gets a bit tricky, right? So why does it get tricky? Because this vol of 3 that I've been able to do every single time that I've defined a new type suddenly doesn't work. So why is that? Okay, so that's because there is no constructor of that type. So it's difficult again to see here. You can see it better in Julia 0.5. So let me do that. So what constructors are available for my vol type now? There's only one, and it looks like this. So what is that saying? It's saying that I can take any argument, but I have to use this parametrized constructor. So what does that mean? It means I have to write it like this. Vol of int, vol with type int in the parameter of 3. Then I can construct a vol with this int type. Okay. So I can construct an object, but that's just painful, right? So the whole point is that I don't want to do extra work, and so Julia should recognize that this 3 is an integer and put it, for me, automatically inside this type. Okay, so I actually have to tell it to do that. So this was done automatically for you by the default constructor, but when you write an inner constructor for a parameterized type, that default constructor no longer is created. So if you want it, which we do in this case, you have to write it yourself. So here it is. So this is a strange looking line, I always thought. And it was only recently that I really understood what was going on. So what is going on? So what does this line say? So the easy bit is in the middle, the equals is an assignment. So it's saying we have a function on the left equals something, so we're defining a function. How are we defining that function? Well, what function are we defining, rather? So we're defining a function that takes one argument, x, which is of type t. But we don't know who t is. So what is t? If we just did f of xt equals, 2x, it would say, oh, hold on, I don't know what t is. Right? So that's what this curly brackets of t is. Again, that's the same syntax as we had in the type definition. Now it's a function definition, parameterized function, parametric function. And it's saying that this is going to be true for any t. So, you could hope that in some version of Julia, you might have \for all tab. That gives me an upside down a, which is the mathematician symbol for all. For all t, define this function. I could imagine writing it like that. And then for me, it makes more sense. For all t, we're going to define what does it look like to have a function called vol with a type t inside that takes an object x of type t. How do we define that? Well, we define it as call the constructor of the type that we have already created called vol with that particular t inside. So this is sort of the most difficult line in this section, I would say. If you understand this, you understand parametric types. Questions? So this is not valid Julia syntax, right? If I execute this line, it doesn't even know what this for all is. So, but that's what is going on in my head. For all t, let's define this function. And so now, what happens when I do vol of 3? So actually, I could even write it a different way. I could write it really like this. So that curly brackets t is sort of in a strange place, in my opinion. It should be sort of outside this function definition. So it's saying for all t, we're going to define volume that takes an x of type t and does this to it. So that's really what it's saying. It's just a notation for instead of writing this funny for all symbol. And so, yeah, so it's really saying for all t, do that. And so when I put the 3 in, what does it do? It says, oh, 3 is an int. So that matches this, this definition as long as I take t to be an integer. And but I can take t to be an integer because I'm allowed to take any type. And so I know that I'm supposed to define the function like this. So when I do this vol of 3, it actually creates a new function, which is a new method, if you like, which we won't see explicitly, but it sort of instantiated that that particular method with int64. Okay, questions? Okay, so that's that. Now we have a version that will work with any type. But maybe we want to specialize, to have a special version for some particular types. So, for example, what we might want to have floating point volumes stored as big floats with high precision. And so we can do that, and we can say vol of any t, which is a subtype of abstract float. So it's any kind of floating point number. For any of those types, we're going to define the function vol as vol of a big float of x. And so now we have another more specialized version. And so when it sees something that matches that more specialized version, it's actually going to pick this method instead of the other one. Whereas when I see an integer, it still picks the other method. It doesn't see this big float stuff. So this is the kind of way that we define generic functions in Julia by this, again, patchwork of methods that act on different subsets of types. And you can see it pretty clearly, I think, in this parametric setting. Questions?
There's no explicit constructor you make for big floats, so there's just this for it, right?
No, there is an explicit constructor. We already defined that one. Well, we didn't, sorry. Julia already defined that one automatically.
But if you do methods, you don't see an additional constructor for big floats.
You do, because it's hidden in this. It's for any type t.
Okay.
Right, yeah, good question. Yeah, so the question was, but where is the constructor that I just used for big floats? Because I didn't explicitly write it. And the answer is, it's this generic one that Julia automatically defined for me, because otherwise I won't be able to create anything.
So it's only when I do like code LLVM and I run it the first time that there will be a specific machine path for the big floats over there.
So the question is,
If I do this for a float, I do this for an int, I do this for a big float, I do it for something else.
yeah.
Those 4 different code paths will only be created on the first
Right.
compilation of any one of those types.
So the question is, when will the code paths, the specialized versions, be created for each of these different parameter types? And I think the answer is when you run the code for the first time with one of those types. Again, this is getting towards the low-level stuff that I'm not good at. Okay, so so now we might want to define arithmetic operations on these types. Right, so we might have a volume, two different volumes of two different objects, and we want the volume of the total object made by putting those two things together, as long as they don't intersect. So if they intersect, it's more complicated. But anyway, so of course, if we do v1 plus v2, what happens? It gives me an error. Why? Because I haven't defined what I want it to do with a plus of two volumes. We know that there's a float or something inside, or an int, but we could do something completely crazy. We could do a multiplication of these things. So Alan Edelman likes the example of tropical numbers where times means plus and plus, no, what is it? Plus, times means plus and plus means max or something. Anyway, so maybe I should have done that example. So you can define them how you like. We could define plus to mean, something minus or whatever. And that might make sense in a given context. So we actually have to define plus ourselves. So how can we do that? So maybe we only want to add two volumes if they have the same type inside. We only want to be able to add two volumes that are ints and two volumes that are floats, because those things sort of work in two different worlds. And we can do that in Julia. So how do we do that? We have to say, so let's analyze this. We want plus a v1 that's a volume of type t, and v2 that's a volume of the same type t. So it has the same t inside. And what's that going to be? It's going to be, I'm going to take the value of one, the value of the other, add them together, and then wrap that in a new object of type vol with the same t again. And I want to do that for any t. And so how do I do the syntax any t? I do these curly brackets t, right, which I would write for all t. And in order to add a method to this plus function in base, I have to explicitly import base.plus. Import plus from base, which is the standard library in Julia, where this plus function is defined. So if I do that, then now I can add these two volumes. So I just defined this function after I had defined the two volumes, and suddenly I can now add them. I don't have to redefine the objects. And it does what it has to do. Okay, but maybe that's just a bit too special, right? Maybe I want to be able to add two things that have integers inside, even if they're not exactly the same type. They're just any integer types. So we can do that as well. So that's more complicated. So what does this say? It says plus a v1 that's a volume of type t1 and a v2 that's volume of type t2 is a volume of some type and the sum of the values again. And that type is going to be what I get by promoting those two types to the smallest possible type that includes both of them. So what do I mean by that? So this kind of promote type is all over the place in the Julia code base. So what's the smallest possible thing that contains int 32 and int 64? Well, it's int 64. What's the smallest possible thing that contains int 32 and int 128? Well, it's going to be int 128. Let's say big int, it's going to be big int. So what's the smallest thing that contains int and float 64? So float 64, because any int can be represented as a float 64, which is not quite true, but is it true? Maybe it's true. No, it can't be true. Yeah, that's 64-bit int. So no, what did I want? Maybe big int. What can I represent with a big? How can I represent a big int in a float 64? A big float, and so on. So there was one. Well, anyway, yeah. So sometimes you get any out. Right? So the only thing that can contain. Oh yeah. So what can contain something of type int and something of type ASCII string? Only something of type any. Okay. So that's what this promote type does. So it's going to. So if I pass in an int and a big int, it's going to give me a big int back. So I'm going to make a vol of that type. And so then, again, if I try and do this, it's going to say error, T1 is not defined. So I have to tell it that I want to do this for any I want to have to, qualify the thing with, oh, damn. I have these type parameters, and I'm saying I want to insist that they're both subtypes of integer, this abstract type that contains all of these integer types. So when I do that, I get this, I get a warning that I wasn't getting before. So this is good that we see this. This is an ambiguity warning that you get when you try and define a function that sort of you've already defined some subset of that function somehow. So I don't want to dwell on that too much, but you can read it, and it says what you have to do, basically. Oh yeah, so I know what it is. Yeah, so here I'm defining the sum of any two types, and before I defined the sum of any two things as long as they were the same type. And so there's an intersection of those two things, which is any two integer types which are the same type. So I actually have to define that beforehand in order to resolve this ambiguity warning. Okay, but I'm not going to do that right now. So if I do that, then I do get the right thing for the integer types. But for float types, I should still not be able to add two, which are strictly different float types. And that's correct. So again, we're making up this patchwork of different functions that cover different subsets of types. And the idea is that's a very sort of, what's the word, standard thing to do in Julia. Idiomatic. Okay, so to, I think, finish basically this section on types. So yeah, so we're doing pretty well with time. So a volume, as I said at the beginning, could be 3-dimensional or 2-dimensional or 1-dimensional or 17-dimensional. So I really want to have that information in my volume object, right? If it's the volume of a cubic thing or it's a volume of an area thing. So I can actually put that straight in the type definition. So I could put it inside the type, that's one option, or I could put it straight in the type definition. So here it is. I've added a parameter n, which is going to be the dimension of this volume, whether it's 3 or 2 or 1-dimensional. So again, because it's a parametric type, I don't get a default, I get a default constructor where I have to specify all of the type parameters. So vol 3 float 64, what is that? It's a type, it's going to be an object that lives in 3 dimensions and has floats as a float as its value. So there it is. So that represents a 3-dimensional cube of volume 3, of magnitude 3. Is that clear?
How do you know that n is not a, how does the compiler know it's not a type parameter? Must it always be the first argument?
So the question was, how does the compiler know that the n is not a type parameter, but rather it's a number? And the answer is, what a good question. Does it always have to be the first parameter? And the answer is no.
Perhaps it doesn't matter because the n you know show up.
Yeah, so what happens? So no, because no, so it doesn't have to be, so it could be a type parameter, right? So if I do this, oh, high tech. So I could do this, vol of int64, float 64, 3, that's valid. So the answer is, it doesn't know. So I don't remember if there's some syntax I can use to tell it that, or if just somehow the way you use it will mess up if you do this other thing. Yeah, good question. Okay. Okay, so why did we do this? Because we don't want to be able to add a cubic volume to a flat volume, to a planar volume. That makes no sense physically or mathematically. So we want to just define plus now for this new type when the dimensions match. So we just do the same thing again. We go through the same process. So we want to define this sum of two volumes with the same n and the same t for simplicity. I could do different t's, which I'm about to do, but let's do the same t first. How do I do that? I get a volume, which is the sum of the magnitudes with the same dimension and the same type. And I have to do this for all n and for all t. And I could restrict those the t later. So we can also, again, promote the types, but keep the n the same. So there's that one. So it starts to look pretty messy, but if you just carefully pick apart what it's doing, hopefully it's now clear. So it's plus, which has for all n, for all t1 and for all t2, define this function that takes two parameters, one of which is a volume of n and t1, and one of which is a volume of n and t2, and it does this thing. Okay, so we can also make just a convenience outer constructor, so-called because I define it outside the type. So I'm going to, for all t, I'm going to define a function vol that takes a parameter n and an x of type t. So I'm not doing for all n here. The n is now a parameter inside, and that's going to do this. And that allows me to do vol of 3 and 4.5 to give me a volume with 3, so I don't have to type out all this stuff. I can just pass them in as parameters. So you have to sit down and carefully think what is exactly the difference between this one and the previous ones I've been defining. Okay, so we also might want to present on the screen the output of creating one of these types in a more pretty way. And so currently, and I think it's going to stay like this, the way to do that is by overloading base.show. So show takes an object of type IO, capital I, capital O, input, output. So we're going to have a little IO, which is of type big IO, an X, which is of type volume with N and T, and it's going to print to that stream, so IO is a stream, it's going to print to that stream the number, and then the string dimensional volume with value, and then the value, the magnitude. So let's call it magnitude. And again, if I try and define that, it'll give me an error because it doesn't know what n is. So I have to do this for all n and t, define this function. So when I do that, when I create one of these things, then it actually prints out something nice, right? So A is vol of 2,3.0. It says what is A? It's a two-dimensional volume with magnitude 3.0, and it's L, which I write with \L tab, just to be fancy, is a linear volume, so it's a length of magnitude 10. And I cannot add those two things because I haven't defined how to add two volumes with different lengths, and I don't want to define that. You might, in some more complicated setting, want to define that as being one thing of this type and another thing of that type, so sort of a tuple. But we don't want to do that probably. Okay, so however, when I actually did this, when I was preparing this, So we want to actually make it an error, make it an explicit error, and tell the user what the problem is if they try to add volumes of different types. So I actually run into apparently a bug in Julia about, it's not clear if it's a bug or just, So how do I have to do that? So what I'm trying to say is I have plus of two of these objects, one of which has one n and the other has another n. I'm going to throw an argument error and say volumes of different dimension cannot be added. But then I'm going to define my other method, which has the same n's, right? So that is a more specialized version, and so it's going to pick that one whenever it matches. And again, I have to do this for all n1, for all n2, and for all t. And so I have to check that it still works to add two volumes of the same dimension, and then that it gives me an error to add two volumes of different dimensions. So this is the kind of thing that you should be codifying or codifying in a test suite. So this is, I'm not really going to have time probably to touch on that, but this is just a fundamental feature of modern software practice to have unit tests that test each of these things. To just test that adding 2 volumes of a given type actually does give you a volume of that same type. Because you might, inadvertently write, like I did, write a too generic version of this function that sort of eats up the other one somehow and suddenly breaks everything. And you want to catch that before you, publish your software or before you run your simulation that you're going to publish in a journal. Okay. So does anybody know if there's a break, or do we just go straight through? Sorry? There should be, yeah. So maybe, I'll just finish this section and then we'll have a little break. Okay, so so now suppose I've just defined this type. So I have this object v1, which is of this complicated type, and I want to take the sign of it. So again, of course it doesn't know how to do that because I haven't told it what the sign of a volume is. Maybe it doesn't even make sense to do that because in some sense it has dimensions, and you don't want to take sign of a dimensional thing, but we'll try and define it anyway. So, okay, so I can do that. I can just import base.sign and define sign of x, which is any of these volume types, as just taking out the value that's inside it and applying the standard sign to that. Yeah, so now I can do sign of v1 and it works. But you really probably don't want to be doing that by hand for every single function in the maths library. So we'll see later with metaprogramming how you can do that in a very easy way. But here we'll look at a different direction. So let's redefine this type again. And what we're going to do is actually specify now that this volume of with a real type inside, well, actually it's a sort of a real number as well. Right, so that's what this extra less than colon real is. We're declaring, oh, this volume object, this volume type that I'm creating is actually a subtype of the reals. So anything of this type will be a real number. And so why do I do that? Because Julia has a lot of functionality for generic real numbers. So let me do that. And then I have this volume, and I can do sign of v, and now I get a different error. And now it's trying to call convert. So it's trying to call convert to the type abstract float from my volume type. So what is it actually doing? I can do this at which sign of v. What is it trying to call? There's actually what's called a generic fallback or catch-all method. There's sign of x for any real x. So it's telling me where that is. I click on there, and I can see exactly what it's doing, except that I can't because it's using this syntax that we haven't seen yet, which is this metaprogramming stuff. So what is that doing? We'll see later that what it's doing is basically saying this. So how do I define sign of x as a real, any old real? I do sign of what happens when I sort of floatify x, when I make x into some kind of floating point representation. So we could do that. We could import base.float and define how to get a float out of our thing by taking the float of its value, and then it works. Okay, that's one option, but that's not really the best option. So what's the best option? The point is that float of this thing is also already defined. So float of x is defined for any x, not just reals, just anything, any old thing. Right? So what does float of x do? It converts x to abstract float. Right? So float of 3 takes 3 and converts it into sort of the closest floating point representation. Okay, so we can actually define that. That's what we're going to end up defining. So how do we convert a volume to an abstract float? So we have to write it like this. So we have to use this : type abstract float. What does that mean? It means the first argument. So we're defining a method. So we have to specify. We could put something in here. Could we? I'm not sure if we can. So it's like having some variable that's of this type. What type? The type is the type of abstract float. So the only thing that has type of abstract float is abstract float. So it's a bit unwieldy, but that's what's happening. And so when we define that, we can now actually convert to abstract float, one of these volume things. And it works. So if you look at methods of float, you'll see that methods of convert, you'll see that there are sort of loads and loads, 500 methods, converting from one type to another, and they all use this kind of syntax. Colon type of this, so that you can pass in the type name as the first argument to convert, like I just did. And so when we do that, now all of the standard maths functions just work because they have these generic fallbacks that go through this convert step. Okay. So I don't know why I did that. Okay, so there we are. So to finish off this section, I should also mention promotion, which is sort of even more difficult to get your head around, or I found that. And it's very difficult to get it right, and so I'm not really don't want to say too much about it because it's kind of tricky, but I'll just give one example. So I decided it didn't really make sense with my volume example, so let's think about a probability instead. So it's sort of like a volume, but it doesn't have a dimension. So probability is just any old, has exactly the same structure, but it no longer has this associated concept of dimension. It's just going to be a real number between 0 and 1. So if we've got this inner constructor, if I'm not between 0 and 1, I'm going to give this argument error and make this object, and then I'm going to do this standard kind of outer constructor. So now I can have these objects, which are probabilities which are supposed to be between 0 and 1. No, I didn't want to do that. I'm going to take out this. I thought I took out the... Right. Okay, sorry. No, I didn't want to do the inner constructor. So we'll get rid of the inner constructor, and we'll just say what we mean by multiplying two probabilities together. So just like we did the sum of two volumes, we're going to do the product of two probabilities, which you can argue it doesn't always make sense in terms of probabilities, but we'll just use it for this example. Okay, so I can multiply two of these things together. So P1 equals prob of 0.3, P2 equals prob of 0.4. What is P1 times P2? It's, oh dear. Okay, it's the product of the probabilities, right? So that sort of makes sense, some sense. Okay, but now what happens if I want to do 0.3 times P2? It does not know how to multiply an actual real number by an object of this type. And so I could go along and define that, right? I could define times for a number and a probability, and then I'd have to define times for a probability and a number, and it gets really boring very fast. And so what I'm actually going to do is use Julia's promotion machinery that we've sort of already seen vaguely at the beginning and hook into that. So this is what I'm saying is difficult to get my head around. So we have to use this thing called promote rule. And what does that do? It tells us if we have two types, how do we promote one? What does it tell us? It tells us to which common type are we going to promote those two things. So this is difficult to process, so let's get rid of, again, these quantifiers. So it's for all S and all T, in some class, we're going to say how to promote something of type S and something of type prob of T. And the answer is going to be prob of what you get when you promote types S and T. And this is going to be true for any reals. So if we do that, And then we have to define convert. So we have to be able to convert from a real to a probability and from a probability to a real. And if we do that, then now we can multiply real numbers by probabilities. So in this case, we see that it actually gives me a probability that exceeds 1. So we would have to go back and figure out how to incorporate that into the type, maybe with an inner constructor or whatever, so yeah, probably an inner constructor would work then. No, it wouldn't. No, I tried that, but it doesn't work because of this 3. So you can't convert the 3 to a probability if you have this 0.1 thing. Anyway, so it doesn't really work as an example about probabilities, but it does work as an example of how you use this promotion, this stuff. And so it's very difficult, I was fiddling around trying to get this right. But once you've got it right, you just leave it there and forever for your given type that you're trying to develop. Okay, so finally, let's just point out that you have to be careful if you want to make vectors of objects which are of parametric type. So let's make a vector, for example, of rationals. A rational is a parametric type. It has this parameter that tells you what kind of integer is inside your rational, your fraction, as the numerator and the denominator. So what is the type of this thing? It's a vector of rationals of ints, or an array of rationals ints with 1. And so, so vector of rational int is just another name for array rational int 64.1. This triple equals tests if these things are identically equal, whereas double equal tests if they're just equal sort of mathematically. Oh. Yeah. So 1 is equal to 1.0, but 1 is not equal to 1.0. They're not identical. They're represented in different ways in computer, but they're equal mathematically as numbers. Okay, so it's true that rational int is a subtype of this abstract thing called rational. However, it's not true that vector of rational int is a subtype of vector of rational. So this is called invariance of types. And so if we define some function that we think is going to operate on a vector of rationals, we'll be disappointed when we try to apply it to our vector of rationals. It won't work, because we actually have to have a vector of rationals of ints, and that is not a subtype of vector of rationals. So it won't be recognized by this method. In fact, this method will never, I don't think it will ever be able to be used, because you can never make a vector of things with of type rationals. You can never make objects in Julia of an abstract type. So all we have to do is, again, parameterize the function itself. So we're going to have, for all t, how do we define the function that acts on a thing of type, vector of rationals of this type, and then it will work. So that's just a side comment, because that's a common problem on the mailing lists. Okay. Any questions? So, sorry that was a bit dry, but I think it was important to do, because it's really a key part of Julia's psychology and technology. So in the next section, we'll look at metaprogramming, and that's pretty fun. So let's take a maybe 10-minute break till 10:50. We'll start again with metaprogramming. Okay, so let's do metaprogramming. So this is really an important, difficult subject in Julia. So I'm going to try and make it as simple as I can. So this was So I've been doing quite a lot of metaprogramming recently. So this is me trying to summarize what I've been discovering. I wouldn't say I was an expert. So what is metaprogramming? So, we should always be scared when some people talk about meta something. Metaphysics is kind of a difficult subject, right? So meta just means we're going to step up a level. So metaprogramming is step up a level from programming. So what does that mean? It means programming something that is going to program something. So I'm going to write some code, and that code is going to actually produce more code. So that doesn't really mean anything yet, but we'll see. So people like to say that it's writing code that manipulates a program rather than manipulates data. So manipulates a program, and maybe it writes a program from scratch, or maybe it takes in a program, some piece of code that was already existed and just modifies it in some way. And then that code is going to be sent off to do some work on some data later. So that's what metaprogramming is. So I wanted to use sort of real, interesting examples to see this. So here's my motivating example. Somebody coming from mathematics and physics background, the other day or a few weeks ago, I wanted to implement an algorithm that was described in a paper, and it was described in standard mathematical notation that looks like something like this. The sum over I not equal to j of 1 over lambda I minus lambda j. So this is for something called Dyson-Brownian motion, so it doesn't matter. The lambdas is just some things that are going to move around, like random walkers basically, that are moving around on the real line and they're interacting, and this is the interaction. That's completely irrelevant. The point is, I wanted to write this in Julia, like this, right? With this syntax. And I can't. And that annoys me. Why does it annoy me? Because what I actually had to write was something like this, which took me a lot longer, and I had to be very careful to get it right. So what I would really love is if Julia could take my nice syntax and turn it into the ugly stuff for me. And then probably I'll have to check that the ugly stuff really does what I want, but at least somebody did the hard work for me, and then I just can go and fiddle with it a bit. So this is the challenge problem for this workshop, right, for this session. Go away and write the package that does this for me, and then I'll give you a handshake. And everybody will thank you when they implement algorithms. Okay, so by the way, this is not Julia syntax, right? I cannot write this in Julia. It will say there's a syntax error, right? So this is not Julia syntax. Let me now be a bit sneaky and put a comma in right here. What does it do now? I execute it, and now I get a different error. There is no longer a syntax error. This is now valid Julia syntax, right? It doesn't mean anything in the Julia language, but it is valid Julia syntax. So we could take this with the extra comma and wrap it in a macro, which we'll see later, and then spit out the code. So we'll see later that we can just take this expression, and Julia knows how to parse it into an actual Julia expression, and then we can just take that apart and sort of cheat Julia by making what we call a domain-specific language, which in this case is going to be the domain-specific language of mathematical formulae, basically. And so that's one thing that metaprogramming is good for, making these domain-specific languages by sort of tricking Julia into using our cute syntax instead of its standard syntax. But it has these little details that you have to add commas or add something in some clever place. So we'll see an example of that later. Okay. So that's too hard to do in this session, probably. So let's do a really simple example. So here's a polynomial that's famous in numerical analysis for reasons that I don't need to go into. And I just want to be able to write that in Julia. No? It's x minus 1 times x minus 2 up to x minus 20. So I can just start out and do it by hand. Brackets x minus 1 times parentheses x minus 2, etc. But of course, if I'm going to go up to 20, I'm going to get pretty bored. In going up to 1,000, I'm just physically not going to be able to do. So, but this is just a repetitive thing to create this thing, this object. So computers, designed for repetitive things. So I should be able to do that just on the computer. So I can define a function that when I evaluate it at a point x does this with a for loop. So here's the for loop, just a standard for loop. So given a numerical value x, this will calculate the value of this function, which is called a Wilkinson polynomial at, of length n at the point x. Okay, and then we can use an anonymous function. Does anybody not know what an anonymous function is? So it's a function that takes x and returns this function of x, and this arrow, which is minus greater than, just x minus greater than this thing, gives me a function with no name. That's why it's called an anonymous function that I can then assign to something. So p of n is going to be a function, and then I can evaluate it at a value. And then, so I have now, written in one way these Wilkinson polynomials. okay? But still, it seems like I should really be able to go back and actually get Julia to write out this expression for me, right? Wouldn't that be nice? Is it clear what I want to do? Yeah? No? Okay, so how can we do that? So that's metaprogramming, right? So I want to write a program that writes some code, some Julia code, namely the product of x minus 1 times x minus 2, assigning it to a function name. That's a piece of Julia code, and I want to write that out. I want to write something that will write that for me so I don't have to write it. Okay, so let's start with the simplest one, x minus 1 times x minus, simplest non-trivial one, x minus 1 times x minus 2. So I'm going to put it inside this quote end thing. There it is. And so what is x? So another possible syntax is with this colon brackets, and then colon parentheses, open parentheses, close parentheses. That's just sort of basically an alternate syntax, although they have slightly different internal representation. So what have I done here? What have I created? This x thing, x from ex, x, read x for expression. So this is actually a thing called an expr, right? So the type of this thing is an expr, or an expression object. And so we can think of that as a Julia code snippet. It's a bit of Julia code, but I've managed to represent it in Julia, right? So x is this piece of Julia code. I haven't evaluated it. It's just the Julia code as an object in Julia, right? So Julia is able to sort of talk about its own code. So this is something that's coming from Lisp, and it's not available in many languages. So this is a very useful capability that Julia has. So if I have a piece of code, what can I do with it? I want to be able to evaluate it, which is basically what happens when you type that code, x minus 1 times x minus 2, at the prompt. And so what happens is, what would happen if I typed that at the prompt, right? So here it is at the prompt, x1 minus x times x minus 2. Of course, it tells me that x is not defined because that's supposed to be evaluating this expression with the value x. So if we give x a value, then I can evaluate this expression that I type at the prompt. Or I can take this code piece and evaluate that, which does exactly the same thing. Okay? So given a piece of code, I can evaluate it. And common programming exercise when I was growing up at least was, I'd love to have something that could evaluate a formula for me. So here's a formula as a string, 3x. And I'd like to evaluate it. I have this variable called x. I want it to multiply it by 3. And it doesn't. It just gives me the string back. Right? So strings are the wrong thing to use in Julia for this purpose. We should use Julia expression objects. Right? So this is a string. So to convert this into an expression, I can use this parse thing. So what is that? It's Julia reading in the thing as if you typed it at the terminal and converting it into the really important object, which is type of object, which is this expression. And then I can evaluate that. And now I have my formula evaluator, right? Okay, so I can just put in an arbitrary formula involving x, 3 sine x. As long as it's valid Julia syntax, right? When I take that formula, let me do it over here. When I take that formula, I first parse it. That gives me my expression. So Julia has worked out that this is valid Julia syntax and has written out in some kind of canonical way. So this 3 sine x is a nice little thing that Julia allows us to do. Just juxtapose this numerical constant with something, and it'll treat it as if it's a multiplication. So here's one of them, and here's another, 3x squared, and we see that it actually wrote those out with this multiplication. This one it didn't write out, but the multiplication is there anyway. And so the parser is already done for us. In other languages, we'd have to sit down and write our own parser. That's pretty nasty. Don't have to do that. Some clever person did that for me. So now I have this expression. I can just evaluate it again, and I have my formula evaluator. Yeah.
How much of a slowdown would it be to actually parse these mathematical equations compared to actually writing them explicitly?
The question is, how much of a slowdown would it be to write my own parser for these mathematical equations? I don't know. Why don't you try and you can tell me later.
Something like writing a parser, just
Yeah.
specifically write a function that has the same form.
Right, specifically write, oh, what? Sorry, right, what?
Instead of writing the equation as a string,
Yeah.
actually write
Oh.
a function.
Oh, instead of writing the equation as a string, just write f of x equals this?
Yeah.
Right, that's fine as long as I don't have to read the string from somewhere else, right?
Yeah, this is what I'm asking, like how much is it slowing down?
Oh, how much does it slow down the process? Yeah, so how much does the actually parsing take? So yeah, I guess it's a bit slow, but usually you'd only be doing that sort of once, and then you'd be evaluating this function lots of times, or it depends on your context, right? It might be that parsing is the most time, and then you have to speed it up, and then maybe you have to write something yourself. Yeah, okay. But usually, that's not my use case, let's say, or it's not the usual use case. Usually you would read in, I don't know, maybe you have some file that you want to write this in that defines your differential equation, and you read that in, and then you solve the differential equation, which is some horrible long calculation, so the parsing time is irrelevant. Okay, so we have this object. It's a Julia object, so what can we do with it? We can ask Julia, this is supposed to be a question. What's inside the object, or what structure does it have? What can I do with it, right? Okay, so there's this function called dump, which dumps out a representation as a kind of little tree of this expression. Or there's another one, which is show s expression, which gives a sort of Lisp type view of this expression. So what's going on? So I changed the expression. I had a much simpler one, right? So let's go back to the simpler one. X minus 1 times x minus 2. So what is the structure of this expression? It's this. Okay, so it still looks pretty complicated, but what it's basically trying to say is that we have a tree. So we have times at the root of the tree, and we have times of two things. One of them is x minus 1, so we have minus of x and 1. And then we have minus of x and 2. So there's the tree representation that it's sort of trying to print out in some ASCII way. So I'd really prefer it to print this out, right? To just draw this tree. So that's some representation, internal representation of this Julia expression as some complicated Julia object that we're going to be able to manipulate with Julia that represents this tree. Is that clear? So this is called the abstract syntax tree. Right? So we don't actually have a tree represented somehow. It's sort of represented in an abstract way, but what we're really trying to represent is some structure that models this mathematical tree, that describes the structure of the expression in a way that I guess Chomsky, who's somewhere in this building or lived somewhere in this building, introduced in the 50s in the context of human language. So, or maybe computer scientists or mathematicians I guess they'd already done it in the context of math. So, okay, so we see that this X thing has stuff inside. So what does it have inside? So again, we can just ask Julia, what do you have inside? So here's what X has inside. It has something called a head, something called args, and something called tip. And then we're going to examine those fields. So x.head is call. So call is, do a function call. And then args are these three things, times x minus 1 and x minus 2. So what does this expression represent? It represents calling the function times with the first expression x minus 1 and the second expression x minus 2. So that's representing this whole structure. But then what we see is that this first thing in x.args, what is it? Well, it's this, is this the operator? Then the second thing is this thing. And what is that? It's actually another expression. It's another object of type expr. And so what we see, and it's clear from this tree representation, is that this little box is another thing of the same type. And so we have a recursive sort of structure where an expression can contain another expression. And that's what allows us to sort of really do neat things with metaprogramming. So we have this recursive structure, and so we're going to use recursive algorithms to basically flow up and down this tree and do interesting things with these structures. Okay, so we can dive further down, right? So again, so x.tab will give me a list of all the things that are in there. So type is this any, so I've never understood what that's for. We're just going to ignore it completely. Okay, and the interesting ones are head, which tells me what kind of thing it is. So for example, if I had a different expression, which was x2 equals, I don't know, a equals b plus c, right? What is the head of that? It's another call. Yes, I didn't want that. No, why is it call? Oh yeah, thanks, x2, yeah. x2 dot head is not call, yeah, exactly. Yeah, it's equals, it's assignment. So that's a different kind of expression. So we can, by analyzing the head, we can tell what kind of structure is inside this expression and then do something based on that. Okay, and then the arguments are, what's going to be operated on. So x.args2, what was that? That was x minus 1. And so that's another expression, and so I can dig down into its args, right? So its args is a list or a vector, an array of type any. Why is it of type any? Because it has some symbols in and this 1 in, which is something of type int. So the only thing that is bigger than, is above symbol and int in the type hierarchy is any. So you could think, oh, but isn't that slow? And so again, we come back to this question of, but we're only going to be doing this process sort of once, so it doesn't really matter if it's slow somehow. Anyway, so yeah, so we're going to dig down into that again. So we see this minus thing, right? So that is the way that Julia internally represents the operation minus, or the symbol x, right? So what is this? The type of this thing is something called symbol. So again, it's this that we came across before. There's this kind of just represents the smallest parts of this syntax tree in an unevaluated way. So it's just a thing called x, right? It has no value. It's not a variable. It's just the thing called x. Okay. So now we have this expression and we know how to go in and look at it. So what are we going to do? We're going to go in and modify it now. Right? And that's where we're getting into metaprogramming. We're going to take some code and make it into a different bit of code. And that's exactly what metaprogramming is. So I'm just going to copy it to make a new one so that we've got the old one to compare it with. So it's now called x2. And we're going to take this thing that was x that we just found and make it into z instead. So we're just going to take that. It's just an array, a Julia array, so I can just go in and change one of its elements. It's not an immutable, it's so I can just go in and change it. So we've changed something inside the object. Let's have a look at the object, and there it is, the new piece of code with a z instead of an x or a z. Sorry, I guess I should use z instead of an x.
Question?
Yeah.
Back up at number 42.
Yeah.
What's the copy? And
Oh.
why can you not just do an assignment?
x2 equals x?
Yeah.
Right, good question. So the question was, why can't I just do x2 equals x? Why do I need the copy? And the answer is because if I now modify x2, so I modified x2, but unfortunately I also modified x. Why? Because that was a discussion I had last year and I really don't want to go and repeat it. Okay, so basically I just have two things that are pointing at the same object. So when I modify one of them, I modify the other. Okay, so that's why I needed copy. So now I've lost the original x, right? Okay, so let's just grab that. Okay. So now I modified it, and so I've now got x2 has been modified and x stayed the same because now I've got two different copies of the same thing that I modified one of. Okay? Oh, sorry, I think I did that in the wrong place. Oh, whatever. Anyway, yeah, so is that clear? So that's the simplest possible thing that you could call metaprogramming. So suddenly it doesn't look so complicated, right? It's just very... So the difficult idea is to accept that Julia is able to represent pieces of code in Julia objects. Once you accept that, then everything else follows as a consequence. The syntax gets a bit nasty, right? So how do I know that x2.args2.args2 is the right thing to modify? So that's where That's where things get tricky with metaprogramming. So you're going right into the guts of this sort of multi-layered object with tentacles everywhere and trying to find which bit of it you want to wiggle and change to something else. So that's where the sort of subtlety of metaprogramming, one of the subtleties, comes in. Okay. And so now if we have these expressions which are different, x and x2, now it's called x2. So now if I define variables x and z, which are the variables that are occurring in these expressions, and I evaluate the two things, I get two different answers because one of them has an x where the other has a z. Right? So this is the point. So now we're going to be able to take some expression in Julia and transmogrify it, transform it into some other expression. Okay? Okay, so there we were just doing one little piece of the expression. Questions? So there we were just modifying one tiny little piece. How could I modify all of the x's to z's? So, these x's are hidden inside this multi-layered hierarchical expression. How can I go in and find each x in there and change it to a z? That's something that you might want to do, right? So I have to actually have some algorithm that I get out of some computer science textbook or whatever that goes through the tree and basically visits each site, each node of the tree in turn, and checks, is this an x? If it is, then turn it into a z. If it's not, then leave it alone, for example. That would be the simplest thing I could do. But I have to make sure I actually visit, in some way, each node of the tree, each sort of piece of the tree. So it's not necessarily, if you're not a computer scientist, clear how to do that. If you're a computer scientist, I guess it's first year or something. So I guess, so that's one of the other things that makes metaprogramming difficult, is that you actually have to think very carefully about how to do these things, and we'll see that later in the in the case study. Okay, so this is what I came up with. So I'm going to have a function called traverse. Okay, so that was an exercise, but I don't really have time for you to sit down and do the exercise, sorry. So function traverse is going to traverse this tree. That's not a very good name. And it's going to take in a function, take in an argument that's an expression. So what's it going to do? So it's going to go through the argument of the expression. Okay, so I'm going to assume, so I'm assuming something already, that this is not already an x. So if this was just an x on its own, then this code wouldn't work. So then you have to treat that as a special case. Well, we're not going to do special cases today, but you have to worry about that if you're doing something serious. So I'm going to go through one by one through the arguments of this expression. And if the argument is an x, then I'll just make it a z. So unfortunately, this is a bit tricky. So you might think that what I could do is just do for arg in enumerate x.args. So enumerate, for those who don't know, does this. So if I have a vector, what does enumerate of that vector do? Well, it gives me this strange enumerate object, which is called a generator. It's a type of generator. So what does a generator do? So it goes one by one through those things. And so I can generically use collect to see all of the things that this generator spits out. And what it spits out is just, oh, that's not a very good example, is it? It just enumerates one by one these things. So it gives me the index, or just a counter, and the value of at the nth. It gives me the counter n and the value at the nth place in the object. So I'm just doing that. So you might think I could do for arg. So let's try that. For arg in x.args, this would be the natural thing to write, right? If arg equals x, then modify arg and make it z. Okay, so if I've found an x, then I'm basically done. Otherwise, if I actually have something that's a sub-expression, so I'm walking down this tree and I've arrived at this node. Okay, so let's do, for example, times of x with x minus 1. I'm walking down this tree. If I arrive at this node and I find it's an x, okay, I just change it to a z and I'm done. If I find it's not a z, but it is an expression, right, this is an expression, sub-expression, then I call the function recursively. So I call the function again on this piece of the tree. So it's sort of another version, another copy of the function that's going to work on just on this piece. So that's the way that we can recurse through these expressions. And then I'm going to go and visit each of these in turn and check if they are x or if they're expressions. So that's what this if is a arg expression is doing. So again, it's probably not the best code, but it hopefully is clear. Then I'm going to call the function, recursively. So if I do that, and I put in this x, and I traverse x, then nothing happens. And that's because of what I changed. So what did I change? So I'm having arg walk through these arguments, and if it's equal to an x, then I set it equal to the z. But unfortunately, arg is actually a copy. It's a copy problem again. So it's now I don't want the copy, right? So arg is a copy of this x dot of this ith thing in the list, and so when I change the copy, I don't change the original list, and so that's why I had I dot arg. So let's just do for I in 1 to length of this thing, and then if x dot arg's number I equals x, then x dot arg's I equals z. Maybe that's a better way to write it. So when we do that, so this is why I didn't want to write it like that, because it sort of gets more messy. So I have to put x dot arg's I everywhere, and then it works. So I've traversed the entire tree, and however big the tree is, this is going to work, and any x is going to be replaced by a z. Okay, like that? Questions? So hopefully you can see already that that's going to be pretty powerful now. So I now have the ability to walk through this entire expression and just do arbitrary manipulations, right? So I'm just going to take this simple version and make it a bit more complicated by saying, okay, I'm going to walk through this expression and I'm going to pass in something that I want to find and pass in what I want to replace it by. So here's my expression, x minus 1 times x minus 2, and I want to replace anything that looks like x minus 1, I want to replace it by x minus 10. Sorry, I didn't evaluate the cell. There it is. I replaced x minus 1 by x minus 10. And what happened to this? Where did the z come from? How strange. Sorry? I didn't understand that.
For the function traverse, the recursive call inside the function.
It's calling the other. Yeah, thanks. It's calling the other traverse that I had already defined, right? Thanks. Yeah, better. Okay, good. Thanks a lot. Yeah. I was calling the traverse that I had to find up here that did something different, right? That replaced x with z. Thanks, good catch. Yeah, it would have taken a long time to find that. Okay. So there we are. So I can just traverse through and replace x by z, and it does exactly what the previous one did, but now it's much more generic, right? Much more useful, just with that small modification, as long as you do the modification correctly. But this is not good enough either, right? Because I can't replace anything of the form x minus a, for any a, with something of the form x minus 2 times a. Why? Because I don't have any way to specify what I mean by for all a, or for anything that looks like a. So what I would need to do that is some kind of stronger pattern matching capability. So I don't think I'm going to cover that today, but we have the correct person sitting in the corner, and Mike Innes, who wrote macro tools that I will talk about a bit. So I think you can probably use that to do that, right? Yeah. Okay, so here's an exercise that, again, I'll leave for after the session, for lunch, right? You have to do this over lunch as part of the workshop. Julia, as you may know, you may have come across and may have been annoyed about, actually, in some applications, uses machine integers to do calculations. So that can lead to some surprises. For example, what is 2 to the 32 times 2 to the 32? Should be 2 to the 64, but it's 0. Why is that? Because it's wrapping round inside a 64-bit machine integer. So we can get, 2 to the 32 times 2 to the 31 is some massive negative number, which is obviously wrong. And you get no warning about this. So you may be preoccupied about this, and you may think that's not a good idea for your sensitive code to, I don't know, do some kind of tracking some satellite very carefully, and you don't want some, whatever code you have, you don't want this to happen. So, oh. Okay, so you don't want that to happen. So it turns out that in base Julia in the standard library, there are checked functions. So what are these checked functions? They are the same functions, but they just do this overflow check. So why are these not in the standard Julia operations? The answer is, as usual, because you have some overhead for this kind of check. And so you're going to slow everything down. And so if you don't need it, then why should you have it, right? You should. So, oh, that was me. Feedback. So if I do this checked mul, I have to actually qualify it with base.checkedMul, then I get this overflow error, and then I can catch that and do something else, like use a big integer in that case or something. Right? So here's the exercise. Go through your syntax, given a piece of code, Julia code, go through and replace plus by checked add, what is it? I don't even know what the names are. Base.checked. Yeah, I can't even do the completion. I think it's checked add. Oh yeah, there we are. Checked add, checked mul, checked sub. Apparently checked div doesn't work because div doesn't have any overflow. Anyway, so you can go through and replace plus by checked add, minus by checked sub, and times checked mul. And then you'll have a way of turning any piece of code that you write into a checked piece of code with no manual intervention whatsoever. Everything is going to be automatic. Right? Is that clear?
Why don't we completely general and do this on all the possible methods for plus?
Okay, yeah, so that's a good point. So yeah, the question was, how can you do that if you want to do it for all the possible methods of plus? So yeah, okay. So I'm being a bit too simplistic, that's probably true, yeah. So you only want to do this if you know that you're only adding integers in your piece of code. That's true. Yes, there's not going to be like a general tool. That would be much more complicated because you'd have to go through and work out what kind of object you were adding, and that's probably a nightmare. It's probably complicated. Okay.
Eventually, it's all going to go down to the integers. Or
No. So the question was, is it all going to go down to the integers? And the answer is, for example, in big float or something, you might be calling out to some library that does something opaque that you have no control over. So yeah, so it's pretty complicated, but if you, in some simple context where you know that you're manipulating integers and you want to be worried about overflow, this is introduction to metaprogramming. So I'm not saying this is the solution, right? This is the idea, and then you have to elaborate it into something more complicated, I guess. Okay. So what other things can we do with meta? So let's go back to what we actually wanted to do. So how do we generate this x minus 1 times x minus 2 times x minus 3? So far we've only gone in and changed something, replaced it by something else. Now we actually want to generate more code. So how can we do that? So we can't do that with these simple methods that we were doing, where we just replace things by something else. So let's start from the basic one, x minus 1. Again, this is a Julia expression. And now we're going to manipulate it and see what we can do with it. So what can we do with it? So we're going to take, so here's an idea. We could take that expression and multiply it by x minus 2. So that's what I've tried to do here. So I'm taking x, multiply it by x minus 2, and make that into a new expression. So what's going to happen? Don't read the text. What's going to happen? What answer am I going to get out? Yeah. I'll just get the ex written out in my expression as a string. So that's obviously not what I want. I wanted to take the value inside the variable ex, and the variable ex being an expression. So it turns out that there's a syntax that Julia provides to do that, which is this dollars. I almost said pesos, which is not right in this country. So dollars EX means interpolate the value of this variable EX, which I'm taking to be an expression object or a symbol, and stick it in there. So this is just the same idea as string interpolation, right? So you can do the same with strings. Let's just recall that. So S equals hello. So if I have, name equals David, I can have hello, the value of the variable name, and it will stick in my name in the string. So in the same way, I'm going to stick in the value of this variable inside this thing that is no longer a string, it's now an expression. And magically, it works. And so we've just built a more complicated expression out of this piece that we had before with a new piece. So we've generated some more code. Pretty neat, right? So we can keep on going, of course. And again, I don't want to do that by hand. So now let's do it automatically. Let's do a loop. So n equals 10, I'll start with where I'm starting, and I'll do this loop. Is that going to work? So I'm multiplying it by x minus I every time. What am I going to get? Yeah, I need a dollar sign. So if I do that, then what does my x give? It gives me x minus I a lot of times, because I was just using this, basically the string or the expression x minus I, and I put it 10 times in with these timeses. So I again need the value that's inside the variable I, which is an expression variable, and when I do that, I get what I was looking for. Pretty neat, right? So I get all these extra parentheses that I might not want. Okay, there's a way to get around that, not using this trick, not using this technique. Okay, so, sorry. I should have, so here it is with the dollars. And I get that. And so now I can just, do n equals 100 just as easily, or n equals 1,000, or whatever. And there it is. Right, so I don't think anybody in the history of the planet has ever written that out by hand, I hope. Okay. Okay, so now we have the right-hand side of the function definition. Now we need the left-hand side. So we want a name for this function. So this one's going to be called p underscore 10. P for polynomial, or W for Wilkinson, or whatever. P underscore 10. So how can I do that? So in Julia.4, I do it like this. Symbol, I'm going to make a symbol, which is going to be p underscore 10, and I can make it from one piece which is a string and one piece which is a number. So n is a number, and it's just as if I had string. It's just like, just as if I had string of p underscore n, gives me the string p underscore 10, symbol gives me the symbol. So in Julia.5, that's now symbol with a capital S. Okay. So then the code that I want to generate, so I like giving it the name code. It's probably not very wise, but maybe it is. So I want an expression, so I'm going to use this expression syntax, and inside I'm going to put the value of this name object of x equals assignment, the value of the expression that I calculated above. And so there is my piece of code that's supposed to represent, or that does represent, the Julia code for how to define a function called p10 that takes an argument x and spits out the thing that I get when I evaluate all of this. Okay? So I've built that up by hand, piece by piece. Is that clear? As mud, apparently. So, there's this extra begin end in there that came because it's a function definition. Okay, so I didn't, and then there's this extra line number information, and there's some extra stuff. But basically, that's what it is. Right? Is that clear? Are there questions? If you understand this, it's sort of, that's it. You've understood it. Okay, so now I'm going to put all that together, and I'm going to make a function. What does this function do? So it's called make Wilkinson, terrible name again, and I give it a number n. So that number better be in a positive integer or whatever, but okay, all those details I'm just leaving out. So, so it starts off, and so it does exactly the same thing, right? It does all of that, it puts it all together, it creates this code thing, and then what do I do with a code object, an expression object? I evaluate it. So this is kind of a bit nasty, but I'm just going to do it right in the function, eval of code. So you have to be careful where exactly these evals work, in which module or whatever that you're working in. So it's not a very good idea to do this, but let's just do it anyway. Okay. So then what happens if we do make Wilkinson of 10, it makes this function p10, right? Because I generated the code to do that, and then I evaluated it. So when I evaluated it, it's as if I typed it at the terminal, at the prompt. If I do make Wilkinson of 100, I get the function p100, x minus 1 up to x minus 100. Okay, so just for fun, I just compared this one where I explicitly created this thing, which is this product, explicit product. So basically, you can think of it as unfolding the loop. So I hand unfolded this loop from 1 to 100 that I was doing in the Wilkinson function. So I'm just going to compare those two functions. So I'm just going to run this twice, basically. So I can. So I'm just changing the range. So I'm evaluating these things at lots of points on a range, and I'm going to change how many things there are in the range. I'm calculating with this at elapsed that you might not have seen, which is just returns the amount of time that each of these took, and I'm just doing the division. So T2 is supposed to be taking more time, I'm claiming. Oh, for goodness sake. Okay, so so F2 uses this Wilkinson function and F1 uses my hand unrolled loop. And we can see that the Wilkinson takes 1.2 times longer, so 20% longer for this range. For this range, about the same. For this range, 20% longer. So it's basically usually 20% slower, the explicit loop, than the unrolled loop. Okay. Okay, so 20% is not a particularly big speed up to go through all this trouble, but it was more for the educational aspect than the speed. Okay, so we've been building. Any questions? Can you speak up, please?
Yeah. So the second function, right, F2.
Yeah.
So for a fair comparison with F2, should we also include the time that it took to create P100?
Oh yeah. Okay. Oh, thanks. Oh right. Yeah. Okay. Yeah. You could argue that. Yeah. So the question was, should I include the time that it took to create P100 in the first place? So yeah. Okay. You can argue about that. Yeah, I agree. But I also didn't include the time it took to create the function Wilkinson. Don't want to get bogged down into those questions. Yeah, but it's a good question. Okay, yeah, so actually benchmarking is a very complicated subject, so Jarrett Revels, who's around, is working on that. Okay, so let's carry on. So we've been building up code starting from something, but we can also build it up starting from nothing. So we're going to start from nothing, which is just this quote end, which is a completely empty thing. So what does that look like? It's an expression. It has a head, which is this thing called a block. And args, what are the args? Well, it's an array of 0 length. So there are no arguments. Right? That's it. So that's literally an empty piece of code. So it's a strange concept, but there we are. And then, okay, so how are we going to add things to this piece of code? Well, we just have to add things inside this args array. So we just go into this code.args. It's an array, it's a one-dimensional array, so I can add things to it with push. So I'm just going to add a equals 1, and then I'm going to add b equals a plus 1. There we are. So I made this piece of code out of nothing by adding bits of code into this quote end block. And now we can evaluate it, and what it did was created these variables a and b in the global space. Right, so you can see that you can really start to do interesting things. And so you can use this, for example, to build up this Wilkinson example as the product of lots of things. So in Julia, you can write an expression a times b times c and look at the form of that expression, and it turns out that it's just times with a lot of arguments. Whereas we were doing, in the way that we constructed it, we were doing times of only 2 arguments at once. And then that result of that with time multiplied by the next argument, and then the result of that times the next argument. So in fact, you can just do times with all of the arguments, and then you can get rid of all those parentheses if you want. And probably that's a bit faster. Who knows? Didn't try it. Okay, so somebody was asking at the break about what to do if we want to sort of do some kind of promotion, but we don't want to use Julia's built-in machinery because we don't have a number. And so one possible answer to that is that we have a lot of very repetitive functions where we want to say what happens when I multiply a number by my object and what happens when I add a number to my object. And probably I have some sort of very standard pattern that just gets repeated. And whenever I have a standard pattern that's being repeated with some variation, I should be using, using the fact that I have a computer that's good at doing that. So we can use these metaprogramming techniques to make repetitive code. So this is used a lot in the Julia code base and in lots of packages. So let's go back to our idea of wrapping a type. So I'm going to just make a type called ourFloat, just for the purposes of this thing, which is just literally has a float inside, and we can make object of that type. But again, we can't add. We don't know what adding these things together means. But of course, we can easily define them like this. We have to import all the arithmetic operations from base, and then just define the plus of an a, which is of type ourFloat, with a b, which is of type ourFloat, as the sum of the things that are inside them. But as I wrote, so this is going to quickly get pretty boring. I have to write all these out. And we don't really want to do that by hand, and we'll probably make a mistake. So we just have to realize that there's some pattern here, right? So what is the pattern? It's operator of a and b equals a.x operator b.x. So I wrote that out here in some sort of pseudocode. So now what we want to do is translate that pseudocode into actual Julia code. So we have this pattern, and the pattern is a pattern in code. And so now we know how to create bits of code in Julia. We can just literally create a bit of code with that pattern. So that's what I've done here. So for op in this list of symbols, plus, minus, times, and divide, again, they're the symbols, the thing called plus, rather than the function plus, right, which is the difference between colon plus, which is the thing called plus, the symbol plus, and just plus, which is the function addition. So op for operator is going to loop through these values. I'm just going to print it out. So this @show macro, if you don't know it, is very useful. It prints out the name of the thing equals the value of the thing. And now I'm going to create my bit of code. Here is the code. So it's basically what I wrote in sort of pseudocode. Instead of this sort of star op star, whatever that means, I'm just literally putting in the value of this operator. And it turns out that I have to put these brackets in for technical reasons. So the value of the thing called operator of a, which is now ourFloat, and b and ourFloat, is the value of the thing called operator acting on a.x and b.x. So that's a way of writing plus. This I could write this as plus of plus of brackets a.x plus b.x. So I'm just going to loop through those and just see if it's doing the right thing, and it does seem to be. So this is the code that it's generating. I'm not doing anything with that code yet. I'm just generating it, and here it is. So what is this? A, which is an ourFloat, plus b, which is an ourFloat, equals a function a.x plus b.x, and it's the same for each one. So that is the correct code being generated. I should always check that before I actually use it. And now we need to just evaluate it instead. So instead of printing all those things out, I'm just going to evaluate it. And so I could put code equals, let's do that, code equals this. So instead of code equals that and then eval of code, I can actually just do @eval, and that does those two steps in one. So I just put @eval, and I put this code sort of snippet that I want to evaluate, replacing op by its value, and now that has actually defined my new methods. So for example, A times B, where A is an outfloat and B is an outflow, now works. Right, so I can just, and I can ask Julia, which method are you using to do that? And it tells me that I defined that in 128 on the second line, so it's this. And so that's what we were seeing before with all these dollars everywhere when we did something like, I don't even remember what we did. What's an example where we can see that in Julia code? I have no idea. Maybe sine of 3.5. Yeah, so there's an example. So for f in all of these functions, which are one argument or unary functions, mathematical functions that have some particular kind of behavior that they might throw a domain error, I'm going to evaluate all of these functions. So sine of x, which is the float 64, well, okay, it's some complicated thing that I'm calling into a C library, and then if the C library returns a nan, which is not a number, then I turn that into a Julia error, Julia exception. So that's, that code that used to look really difficult suddenly got a lot clearer to me. Is that true? Now that we know what all the pieces mean, you just have to sort of pick it apart, bit by bit. Okay, so macros, these at things. So we can actually write our own macros. So what is a macro? So it's basically, as far as I understand, just what we've just been doing. So a macro is like is sort of like a function, it's sort of a super function. So a macro is a function, in a mathematical sense at least, it's a function that takes in an expression and returns an expression. So it's just exactly what we've been doing. We took in x minus 1 times x minus 2 as an expression, and we returned z minus 1 times z minus 2. So we had a function that did that. It took in an expression and returned an expression. So a macro is slightly different. What does it do? So let's define the simplest possible macro, called simple. It takes in an expression, and it's just going to print out the expression and then return nothing. So what happens if I put at simple of x plus y? What's it going to give me? Okay, it's going to return nothing, but it's going to print something out. The value of this expression that it's receiving. Does anybody guess what that's going to be? So this is the key point about macros, or one key point that you have to understand. So what the macro receives is the parsed code x plus y as a Julia expression object. So this is sort of how Julia allows you to write domain-specific languages. Right? So I could write here x. Could I write this? No. So we have emoji completion, which is a completely useless thing. That's just quite fun. Okay, so let's try something else. So x less than or equal to, no, that's not a good example. I want some sort of strange mathematical symbol that is valid Julia syntax. Okay, there, for example. Right? So that is valid Julia syntax. It's one of these LaTeX symbols with a twiddle underneath. That does not mean anything, right? If I do x equals 3, y equals 4, x twiddle y, it'll say twiddle is not defined. I can go and define that if I want. But the point is that now but Julia is happy to parse it, right? So that thing exists in the Julia parser as an infix operator that goes between its two arguments. And so that enables you to have the liberty to use this in your program to do what you want to do with it, to mean some mathematical object or some whatever. Okay, so the point is that inside the macro, it has already parsed the expression for you. Right, so at simple of 3x squared plus 4x minus 2, you receive the parsed version already, and that's the point. Okay. What happens if we redefined the macro to not only print out that expression, but also return it? So I'm just taking an expression and returning the same expression. What do we get then? Oh, that wasn't very clever. So let's go to w plus z. Yeah. So W is not defined. So what's happening is the macro returns the expression, and then it gets evaluated. The result of that, what the macro returned, this expression, automatically gets evaluated. Right? So there are two sort of extra steps happening when you're using a macro instead of a function, a standard function. So the standard function receives an expression that you have to explicitly type as a Julia expression and returns an expression. A macro receives an expressionified, a version of what you typed turned into an expression, provided it's valid Julia syntax. It works on that. It returns an expression, and that expression actually gets evaluated. So what is happening is that the macro receives this piece of code, and that piece of code is, with the macro call, is replaced by the new expression that the macro has created. That all happens before anything gets compiled, touched by the actual Julia compiler. Right? So that's the point of the key point about macros. So we can, for example, so we had this traverse thing before. So now we can have a macro traverse, which takes my traverse function that I defined. So the macro traverse is going to receive an expression. It's going to pass it to this traverse bang function that I defined, and then it's going to actually return the quoted expression. So let's just return nothing for the moment. And so there we see that it received the expression x plus y. That expression, so I didn't ever have to type the sort of the colon parentheses. I don't have to type that. That's done automatically by the macro, or in the process of passing the thing to the macro. And so then it passed that expression to traverse bang, that traversed the thing, replaced all the x's by z's, and and then there's meta.quote is if I want to return the quoted, so I want to return actually from the macro, I want to return the actual expression. So that's something you usually don't want to do. The point is that if I don't do that, and I just return the expression, then it's going to evaluate again the expression, which you usually want to do. So you have to sit down and think about this several hundreds of times, and then hopefully it'll become clear. So there's this thing, how do I know what a macro does? There's this thing called macro expand. So I pass it a Julia expression. So for example, at time sine 10, as we all know, calculates sine of 10 and tells you how long it took to do it, right? So there it took a long time because it was compiling stuff. If I do it again, it takes a very short time and it doesn't allocate anything, and so now I know that it's already compiled, and so it takes a short time. So what is this at time doing? It's taking the expression sine 10 and it's right, it receives the expression object that looks like this, sine 10. That's what the argument inside the macro has become. And now it does something to that and returns the new expression. So I can see what it's doing with this special macro expand function. I pass it an expression object and it returns this. Okay, so it's a bit unreadable, but you have to know that these hash 101 hash stats, that's just an internal representation for a sort of for a variable with a unique name, right? That hash 101 is just a way of making a unique name. And so what it's actually doing is that. So we can see that in here somewhere hidden is sine of 10. So I have my code. I'm just putting val equals that. So I have some local variable called val. That's, so it wrapped this. It generated the code to do val equals sine of 10. And then around that, it did all this other stuff with these timing functions. So that's what the macro is actually doing, sort of inside. We can actually go in and just look at that. So here's another example. So this comes from my one of my main packages, validated numerics.jl, which does interval arithmetic. So we don't have to really know what that is. Oh. So I've been trying to reinstall various things recently, so I haven't managed to run these packages recently. Okay, so it creates an interval, literally an interval of real numbers between a lower bound and an upper bound. So I have this at interval thing. So it's taking this 0.1 and doing some magic that I'll talk about on Thursday maybe a bit. So we can see what it's actually doing by doing macro expand this. And so it's actually converted, so it receives this 0.1 and wraps it in something else. And what it's wrapping it in is this convert. So it's doing convert 0.1 to an interval with some type, which in this case is float 64. And so if I do something more complicated, it's going to take this whole expression as a Julia expression and do the correct calculation with intervals. And what that's doing is this. So it's hard to read because of these validating numerics everywhere, but basically it has this structure. Sine of, and it wraps around this sort of conversion of this number to something. So if you've ever had the situation where you have an expression or you have some structure and you want to go in and sort of wrap something around the individual bits, then this is a useful way to do it. There's some subtleties because, for example, 0.1 is parsed before you get it in the macro. It's parsed to be a float 64. So that leads to some issues that I won't go into. Okay, so now we can take the checked arithmetic function that we did before in your homework, and now write a macro that's at checked. So now I can just take a piece of code, put at checked on it, and then have this checked arithmetic version. Yeah. Oh. So the question was, can I do this macro expand and have it printed out in the other form, which is this, you mean the dump form? I don't think so. Because this doesn't actually return. Oh, yeah, it does. Yeah, so that's actually returning the expression. So now I can just do dump of that. Yeah, great. Thanks, good question. So that's the exercise. Okay, so now there's this important subject that I'm not going to say anything about, mainly because I don't understand it well enough, which is macro hygiene. So I don't really like the word hygiene, but that's what it's called. So again, this is something that's well known in Lisp or other languages, so there are lots of books about it. If you go and look at a Lisp book, maybe that's a good way to understand it. Basically, the idea is that in a macro, you might have some local variables, and those local variables might have the same name as some variable that you're wanting to manipulate in the code that is calling the macro. And so you have to tell it sort of explicitly whether you want to use the local one or the external one. And so that's what's called escaping. So you want to allow some of the names that are inside the macro, some of the symbols, to escape from the macro context and refer to things that are outside in the real world, or in the outside world. And so that's called escaping, and it's done with this esc word for escape. And so I always have to just fiddle around and see where I put the esc. I don't have any good intuition for that yet. So I won't say anything more about it. And there's some documentation that might help you. Otherwise, you have to sort of look at a lot of examples of people using macros to see where this escaping might happen, or you can talk to some more people who are more expert than me. Okay, so I guess I've got about another 10 minutes. So I'd like to do a quick case study that comes from this interval constraint programming package. So what is that? What does that do? So it does this thing called interval constraint propagation. So the idea is I have a constraint like this, x squared plus y squared is less than or equal to 1. So that represents some set in the plane. So in this case, it's a circle. But that's and so I want to know what is the set that constraint represents. And that's a pretty difficult question, actually. And so I want to go from this very high-level sort of abstract way of thinking about it to some concrete code. So I want to take this expression and create another expression, which is a piece of code that does something very concrete that actually somehow represents this set. And what it's going to do is So I've got a circle. What it's going to do is take a box, square box, and it's going to actually tell me which pieces of this box are inside or outside the circle. How's it going to do that? It's going to take the box and squash it still to be a box, and that box is going to be, let's say it's going to be the smallest box which contains the piece of the original box that is inside the circle. In other words, this piece, the intersection of the original box and the disk, is going to contract my big box to this new box, which is, I don't have any colors. The smallest box that contains that piece. So it's not clear how to do that, but some people have invented an algorithm, and it's what's called interval constraint propagation. So I don't want to go into the details, obviously, but I just want to show a bit of the flavor of the code. So we have this expression, x squared plus y squared, and what we're going to just start off by is actually introducing new variables in that expression at each node of this abstract syntax tree. So I actually want to have a new variable that lives here. Z1 equals the result of doing this minus of x and 1. In other words, Z1 equals x minus 1. So Z1 is just a dummy name. I'm calling it Z1, but I could call it some other more complicated thing, or I could use one of these really complicated names that we just saw. But I'll just keep it simple with Zs. So I want to convert this expression into this concrete piece of code that does something. It takes an x, it takes a y, they're going to be these intervals, and it manipulates them and gives me a new interval called Z3 at the end. Because they're going to be used later to pass the information back about the constraints. That's why it's called constraint propagation. Okay, so we have this expression and we have this structure of it, and what we're going to do is, again, walk through this structure and do something with it. So probably I'm not really going to go into the details. So I just read a little function that takes one of these constant global arrays as the way to generate these new symbol labels, and a function to make a new symbol. Right? So if I make a new symbol, I get this Z1 out. If I do it again, I get Z2 out, etc. So each time I call make symbol, it's just going to throw a new symbol out that I'm going to use every time I hit a new node. Okay, so what do I have to do? So this is the code. It's actually not that long once I manage to simplify it down. So it's going to walk recursively through this tree. But it turns out that the way the algorithm works, it has to go to the bottom first. It has to go all the way to the bottom and start there, introducing the variables. So it's going to go down, introduce a variable here, introduce a variable here. They're both at the bottom of the tree, the leaves. And then it's going to go back and introduce a new variable in terms of the variables that I just defined, which represent the children of this node. So that sounds kind of complicated, and it is until you work out how to do it. And so, but I can sort of sketch out the structure, at least, of the idea. So I have an expression, and I'm again going to suppose that it has some operation, some main operation in the expression at the top of the tree. And then, so I'm going to build up some code from empty again. And so first of all, I'm going to process the nodes, process the children nodes, the child nodes. Why? First of all, because I want to get to the bottom of the tree. So I guess this is depth first exploration of a tree. So first of all, I'm going to process the child nodes. And so how do I process this node? I process its children. So the first thing I'm going to process is an x. So I've actually got a catch-all unfold of something, so where this x is anything. So in this case, it could be a symbol, or it could be an integer, or whatever. And that's going to return the symbol itself and an empty code block. Right? So the idea is that at each node, I'm going to build up a piece of code here, a piece of code here, and I need to know these variables, the sort of top-level variable at the top of this sub-expression. And then here, what am I going to do? I'm going to join together those two pieces of code, one after the other, and then add this new expression in terms of these top-level variables of the children. So that's the sort of overall picture, and this is how I do it. So I first traverse the children, and I store, they return variables, the top variable, and the whole code that the whole subtree has produced. And here I do the new line as z3 equals z1 plus z2, and I just stick them all together into this new code object.
This traverse should be unfold, right?
Thanks. Yeah, thanks a lot. Okay, so let's try it. So unfold, oh, there it is. So here it is. Does it work? Yes, it does. So z3 equals x squared, z4 equals y squared, z5 equals z3 plus z4. So obviously I'm going very, very fast, and I'd prefer to go a bit slower, more slowly, but I have to finish. So, but at least I hope you get the sort of overall picture. I think this, I boiled it down as simply as I could. So this really does this, walking depth first down the tree, introduce these new variables, and then do it all in the correct order for the algorithm, for what the algorithm says. And now, what do I have to do? I take the thing at the top, the Z3, and I introduce the constraint on it. The constraint just says that it lives in some set. So for example, x squared plus y squared for the disk, the unit disk, x squared plus y squared is less than or equal to 1, that's the constraint. And so here's the constraint. Interval is this interval object from my package between 0 and 1, and I actually just have this intersect operator. So that's an operator in Julia that you can use for your purposes. That's aliased. So you write it as \cap tab, and that actually is just another name for the intersect function, which is in base Julia. So I can override that, overload that for my intervals. So I have an operator which finds the intersection of two intervals. So there's the new piece of code, and then okay, so I shouldn't have done it twice, but that's the new code that imposes the constraint at the top level. So, and then I have to push that constraint down. So how do I do that? So it turns out, so what's the point? So the point is that if I know that Z5 equals Z3 plus Z4, right, which it is, then that means that Z3 equals Z5 minus Z4. And so we can push the information about Z5 down onto Z3 by doing Z3 equals Z3 intersect Z5 minus Z4. And so, so that's called a reverse mode function. So it's sort of like an inverse function, sort of the opposite function. So, so they're defined in this place with these names, which I've just changed actually, but whatever. Yeah, so we want to do something like this. We want to replace, okay, so now we want to take the piece of code that we just generated and actually go backwards. So we go back along the chain of pieces of code, of lines of code, and take them one at a time, but in a backwards order, and apply these sort of reverse operations. So here's the thing that does that. So if we have really. Oh, so I have this dictionary that sends plus to its reverse operation and minus to its reverse operation. And then, oh, yeah, so it's more complicated than I didn't actually run this piece of this stuff. Z equals x plus y, let's do. Okay, so it replaces this z equals x plus y with zxy equals reverse add zxy, and then that's some function that does this intersection. And so then you go along, you do it for all of them, and that gives you this interval constraint propagation. And so that actually, that interval constraint propagation that we've just programmed, or almost, does this contraction operation, amazingly enough. Right? That's the idea. So we have this constraint, we sort of propagate it through these intervals, and it contracts this box. And so we turned this declarative constraint into an actual algorithm that does something and tells us which piece of the original box is inside the disk, basically, roughly. Okay, so just to finish, this looks very messy, and it is very messy. And so there's actually a better way to do this using Mike's macro tools package. So, because you have to really go in and know which pieces are the operator and which pieces are the in the assignment are the whatever the plus, and it's all very messy. And so there's this sort of pattern matching way of doing it, which is to say I want to match my expression to something which looks like something equals operator of something comma something. So you put these underscores here, and then you put this equals greater than. That's one of these domain-specific languages I was talking about. So we're sort of stealing Julia's syntax to do something different. And then you just return the list of things that you want to capture from this match, and you store them in these variables. So you need to using that. I have my expression, and it managed to extract out of that in a sort of simple way. So macro tools managed to extract out of that expression in a really more simple way all of these variables that I need in my code. And so another exercise is to finish writing the backwards pass using all this information. Okay, so I'm going to stop there, unless there are any questions. So thanks for your attention. Have a good JuliaCon.